Hi, I'm Aaron Contorer. I'm the founder and CEO of FP Complete, which is a high-end software engineering tools and capabilities company located here in San Diego. We're about 5 years old. And we focus on tools for developer productivity and DevOps productivity. And engineering methodologies that go along with those tools. So we try to help companies that are building and deploying custom and semi-custom software to be more successful at what they do. And in a minute, I'll get to what Etienne said, which is a little bit about my background. But I wanted to explain the premise of today's talk. We all, I'm a former CTO, now CEO myself, and we have a lot of CTOs in the room. We all want to hit that sweet spot in engineering. Whether we're developing, deploying, operating, maintaining software, we want to make all three of these circles true. And it's extremely, extremely difficult. This is a variation on the famous engineering triangle. Do you want it good, fast, or cheap? This is a different way that I like to show it. Do you want to produce a lot of great software all the time and get it out there? Or do you want it to be of high quality and able to handle a lot of load and not crash and not have security holes and so on? And if you want both of those, well, what about performance? Because a lot of the tools that are quick don't make high performance software, and a lot of things that focus on quality can impact on performance or on productivity. So these are all things we know we want, but they're all things that we find tend to conflict with each other. But I have a thesis which I have used for many years now in my career, which is that tools dominate our work. We, in fact, spend most of our time building and operating tools, and we run factories for technology that are based on tools. A car factory without the equipment isn't a car factory. It's a bunch of people who wish they had a car. And a software group without great tooling isn't a software factory. It's a bunch of people who wish they had some software that they could ship. But if you look at how tools evolve over time, there is no limit to how they evolve. They just keep getting better. And you can imagine that the factory that has a computer numerically controlled cutting table really doesn't resemble in any way the factory that has a handmade hatchet for cutting wood. What they're capable of building is completely different, and all their processes are different. So my talk today is going to focus on a couple of areas in which tools have gotten dramatically better. Functional programming for writing code, and DevOps for deploying and operating code and making it scale. And my thesis is that tools dominate everything else we do. We can completely revolutionize and transform our ability to achieve the goals that I just spoke about if we have better tools. And a lot of these tools are ready. I also have a subtler thesis, which may be hinted at only in this presentation, which is that there are deep architectural truths behind why these tools work. Truths like immutability, truths like making the computer do the work, truths like semantic meaningfulness, truths like reproducibility. So I'm going to suggest, although today's presentation won't touch on it in too much depth, that functional programming and DevOps are in fact two tips of the same profound iceberg, that there are deep architectural improvements now afoot to how we make, deploy, and operate software. And so we're going to look at two of the technologies that my company, FP Complete, has spent the past 5 years working on ourselves and working with a variety of high-end engineering clients. A little bit of background so you can decide for yourself whether you want to listen to one or another thing that I say. So my career in software began in the early 80s when I co-invented the idea of shareware, which is now called freemium software, the idea that you could give people software to download and then they could pay for a better version if they wanted. So I was one of 7 or 10 people that year who invented the idea concurrently back when people were downloading software on 1200 bit per second modems on their phone lines. I went on to be a developer at the National Center for Supercomputing Applications back when they had a Cray XMP supercomputer that was about as powerful as your phone that was being used for advanced physics research and had a whole floor of a building dedicated to just the 24 gigabyte storage for that supercomputer. So I've been doing software for a while, and at NCSA I worked on a product called NCSA Telnet, which was the predecessor to both Mosaic and Internet Explorer. I went on to Microsoft, which successfully convinced me to go there. because my manager from NCSA had gone there. And I worked as the program manager for distributed systems, distributed security, and distributed storage on technologies that made their way into being important parts of Windows, a server, and Microsoft Exchange, the messaging and directory service server. I went on from that to be the architect for the back end of MSN, Microsoft's online services. And actually, the document called MSN 2.0 architecture was written with these hands. That went pretty well, and so I got shanghaied against my will to work for a gentleman named Bill Gates. I say shanghaied because I love running software teams, but he said he needed a technology advisor, a sort of technical assistant. So I had the great privilege. I was stupid to reject the job 3 times, but eventually was told I would take it anyway and was glad that I'd been forced to. The great privilege of working for Bill directly for over a year and learning about sort of how everything is done across Microsoft, and couldn't have asked for a better educational experience. And to this day, I don't know why they paid me for that year. I should have paid them. Bill then asked me to run Visual C++, because this was at the time that Visual C++ was the world's leading tool for developing software, but was under great threat from a crazy new tool called Java. And Microsoft was afraid that perhaps it was true that purely cross-platform software was going to make Windows irrelevant. So he asked me to go work on Visual C++ and run that and part of Visual Studio to see if we could improve what people do to make software. And of course, Microsoft's own products like Windows and Office were built in Visual C++. While running that group, I learned the importance of tools much more deeply than I ever had before. And I learned that products like Windows and Office, which were responsible for most of Microsoft's revenues, were woefully behind. When I say woefully, I mean 1 to 2 years behind schedule. Windows 95, the original name wasn't Windows 95. It was supposed to ship sooner. And so I found a lot of the engineering managers around the company were saying, we need much more than just C++. We need much better tooling if we're going to do our jobs. And so I looked for a person to build and run a productivity tools team to create the IT that was needed to deliver large, complex software products out of Microsoft with that generation of technology. No one was willing to volunteer. It was such a scary job. But I guess Bill had earned my loyalty enough that I said, well, then I'll volunteer until you can find someone more suitable. And I ended up building and running that to about a 65-person productivity tools team, serving the 4,000 engineers that were building just Windows and Office. And that was a success. We made Microsoft about $300 million in cash savings in the first year, just through productivity increases. And that's when I knew that I'd be a tools guy forever. I went on to work at various startups after Microsoft and spent, probably with Bill as a bit of a role model, some time as just a philanthropist, trying to give away some of the money that Microsoft had generously given me with stock options. But I loved this industry too much and jumped back in to serve for about 3.5 years as Chief Technology Officer at Everyone Counts, which is a secure online voting services company, also here in San Diego. They do congressional elections, the Oscars, and other sorts of interesting elections. And there at Everyone Counts, I started to learn about the problems in modern tooling that led me to get really into the tooling business as a CEO and to found FP Complete. And what I learned was that programming still sucks. We had a great team of people, that company still does, building software for very high stakes uses. I mean, literally people get elected to Congress, because of the votes that are processed by their system. So the security and quality is paramount, and the availability is also absolutely necessary because elections end on one day. So a great deal of voting happens on a single day, and if you have downtime during that day, you may actually affect the outcome of the election. And what I learned was we were wasting our people's time and talent not building new features. It took almost everything we had just to deliver software that was robust enough. And people were spending their times dealing with type signatures in Java, writing the same code over and over and over again. People were spending their time with obscure runtime errors involving state or interpretation that's only visible at runtime that could never be found statically at compile time, and chasing down why is this variable different 1% of the time. And just our best people were spending their time fighting against their tools instead of focusing on building online election services, which the world, frankly, could use more of with as much security as possible, as we all know. So I decided there must be something better and decided that as CTO, it was my job to choose the tools that were going to change our lives. And so I started looking at modern engineering tools, which I had been distracted from by first philanthropy and then distributed systems security engineering, my other sort of software love. And so I got back to say, well, where have development tools gone in the last little while? What have we learned? And what I learned is people were raving about functional programming. The developers using functional programming, a variety of different languages, were saying that their lives were completely transformed. They were saying their productivity was up by 100%. Literally, I saw some saying their productivity was up by 900%, that they had 2 people doing the work of 20. It was just shocking things that people were saying, and they were credible people. So I looked at what were the most popular languages, downloaded them, wrote code in them, went to online forums, asked people how it was going, and I learned that functional programming was for real. So I decided that I'd better spend more time on that. So in today's talk, we're going to hear very high-level stuff, and I want to be very clear, this is a management-level talk, okay? You people are responsible for driving the ship. So this is not a talk where we're going to be writing code. This is not a talk where we're going to be even launching a single command line on screen. This is a talk about fundamental principles and how they may affect the ability of your companies to save thousands of engineering hours. This isn't about a clever new command line flag that we've learned about. So functional programming first. First of all, some people here know what functional programming is. Does anybody feel confident enough to give a very brief definition that would help the rest to know what it is? I can define it if nobody else wants to, but anybody want to volunteer? Please go ahead.
Just basically running something where none of the state in what you're running ever changes, and it's sort of linear, so you never have to worry about processing objects. You never have to really worry about state at all.
That's a very important part of the definition of functional programming, probably the key part. It's a stateless way of programming. It's a way of programming, as I've put it here, where you define your program in terms of things that are inherently true based on algebra. So a functional program looks like verbose versions of this. A function of this input by definition equals these outputs. Now that might look like the syntax of some other programming languages, but it's not the same thing. So I want to distinguish the way we typically program today from functional programming. Today we program typically in languages that all fall into a category that goes back to the very first languages ever created for computers, and they're all called imperative languages. And an imperative language issues a series of commands to the computer. It says first do this and then do that. As you've nicely said, that whole dependency on state is implicit in that. In other words, if I have to do this command before I do this command, there must be something in my head about why this command went before that command. But whatever that assertion is not visible in the program. So ordinary imperative programs have implicit state even as you just move from a line of code to another line of code. If the computer were to decide to execute that program, let's say, quickly, perhaps doing 2 things at once using multi-cores or other forms of optimization, maybe out of order or speculatively, the program would not work. And we find that again and again as we try to take old-fashioned programs and move them onto faster hardware. They don't work anymore. I had an interesting conversation with one of the executives at Goldman Sachs who said they had a program that could trade automatically on the stock market. And in theory, in the lab, it makes money every time you run it. But when you put it on a full-size cluster with more CPUs, it doesn't work anymore. Why does that happen? Because in imperative programming, we really don't tell the computer what we were trying to do. We just tell it to do a series of steps, and our mental model is that that series of steps would yield something which must be correct. In functional programming, which we're not going to learn today, because I'm just going to point you at some web resources, you're smart enough to do that yourselves, we simply give parameters, define a function, and say the result of this function is definitionally always true with respect to those parameters. There's no dependency on state, which means, thank you for the word, functional programming relates to immutability. Functional programming, the code lives in a world that is without time. You can call a function anytime you want. It's always true. You can delete the function and substitute in the contents of the function instead of a function call. It will do the same thing. You can prove 2 functions equivalent and substitute one for the other. It will do the same thing. Functional programming is a series of statements defined by you that you've said are always true. So what is the square of x? You take x and multiply it by x. That's definitional. That's going to be true no matter when you asked. So functional programs don't do input. They don't do output. They don't look at the state of the world. They don't modify the state of the world. They take all those sort of goofy functions that look outside the world of inherent truth and math and quarantine them into a little I/O zone of the program. And the rest of the program is inherently true. What that gives us are programs that are inherently bug resistant and optimizable. I'll speak to a couple of examples in a moment. But most importantly, programs written in the FP languages are much shorter much more reusable, and much faster and more parallel than programs written in the languages that we're used to using. And yet, despite all these things, they have fewer bugs because we've asserted inherent truisms that the compiler can catch if we ever try to violate them. So functional programming allows us to achieve the impossible trio that I talked about before. Developers using functional programming consistently are saying that they are thrilled, they're delighted. And I remember when I was first researching Haskell, which is the language that my group, FP Complete, decided to go with primarily, people were saying things like, now when I have to use Java, I feel like I'm being punished. The difference is that large. And the 100% or more productivity gains are not exaggerations, they're true. So I say to you now, if your company isn't using functional programming, you will be. You'll either be using one of the functional programming languages, like those that I've listed on this slide, or in the very worst case, you'll be using a traditional language with functional programming capabilities tacked on top of it, which can be done. Before I go on to talk about some examples of functional programming in action, I just wanted, because I know people care a lot about being able to move forward with good ideas, not just hearing about a vague idea, I wanted to speak about some of the specific languages because I and my team spent a long time on this issue. We've firmly decided that Haskell is the best functional programming language currently available. I want to say that with absolute firmness. It's a fabulous, fabulous language. It hits all three of these benefits. The productivity with Haskell is unbeatable. The performance is as fast as C++ on a good day, sometimes even slightly faster because of the optimizations the compiler can do. As fast, I want to say, as parallel, inherently multi-core C++, which actually doesn't exist. So it's faster than C++ in many cases. And yet the code quality is magnificent, and you write about 20% as much code as you would in Java or C++. We love Haskell, love it to death, highly recommend it. In fact, we are now the leading open source supplier of Haskell tools in the world because we like it so much that we try to give back. But I also want to recommend, if for some reason you are working on a platform where native code doesn't work for you, there are three other very strong functional programming languages that are definitely worth a look. On the JVM, Clojure is a very good language. On .NET, F# was written by a team that was directly informed by Haskell and basically tried to merge ideas from Haskell with ideas from C#. That said, F# is not becoming popular, and so Microsoft over time is trying to work more and more of its features into C#, but it'll be a long time, if ever, before C# is a real FP language. So F# would be what you'd look at on .NET. And Erlang, which runs on a sort of a proprietary runtime, comes out of Ericsson. They wrote the language themselves for their own use, and then they found out it was useful to other people. It's not as fast, but a very high quality language. Worth a look, at least, if you don't like the others. But strong recommendation for Haskell if you're okay with something that writes fast native code as opposed to JVM or .NET code. Also very famous in the world of functional programming, along with Haskell, the other biggie, the other big name is Scala. Scala is a variant of Java as C++ is a variant of C. Like C++, and I say this as the former head of the world's #1 C++ product, so I say this in good faith, it's a catastrophe when it comes to writing bugs. Both Scala and C++ are fabulous ways to write bugs, and you can write code that even other members of your own team can't read, and even you yourself, 2 years later, probably can't be sure what it does. The reason I do not recommend Scala in particular, and if you search that phrase, you'll find the #1 open source contributor to Scala saying it better than I can, is that Scala code is not semantically correct, and it contains all kinds of hidden assumptions about side effects. So as the key point of functional programming is statelessness, Scala tries to be Java compatible. Java is a profoundly stateful language in which calling a function 2 times can yield 2 different results because the function may be maintaining static data secretly in the background. So Scala doesn't work as a functional programming language. As a variant of Java with more features, sure, it has definite merits, and you can write good software in Scala. But if you really want to do functional programming, I would look at one of the first 4 languages, especially Haskell. And a quick shout out to OCaml. The community hasn't embraced it, but it's a nice piece of work too, so good for them. Sorry for them that it hasn't been adopted more. Look at one of the first 4. A few quick stories of things we've really done, all involving FP Complete, on functional programming. We wrote an online IDE in which people could, in secure compartments, edit online with an editor in the browser, build and run cloud-based programs. We built the whole thing with a team of about 5 people. We built it in about 9 months, and it ran on AWS, including automatic scaling and automatic deployment of applications to other cloud servers where they can run. We did that with that level of productivity, and then once it was deployed on Amazon Web Services, it ran unattended, with no manual intervention for days at a time, with hundreds of members of the public building and running arbitrary code at their own discretion inside our system on AWS using ordinary Linux as the operating system. And it worked. The productivity we found with Haskell, which was the language we used to write this Haskell tool, was just absolutely immense. There's a FP Haskell Center version 1 is the one I'm talking about. It's been deprecated, but there's a version, there's a video on YouTube that you can see that shows you all the features that our tiny team was able to make in way, way less than a year. Another project we worked on, much larger even than FP Haskell Center, we co-developed with a large pharmaceutical company a predictive oncology system. And when you get the slides, you'll see there's a link there if you want to read a short paper about it. And it's a system that does high-performance computing to predict how patients will respond to different medication programs, different cancer patients being medicated. You'd like to experiment on a computer rather than on a sick person, right, if you're a doctor or a scientist or so on. So we built this system in Haskell, including enormous cloud scalability. So using Haskell's built-in functional programming-based multi-core support, we can run this computation on 36 threads, 36 hardware threads on 18 dual cores, on the largest compute machines that AWS can provide. And then we wrote some libraries using message passing, because the functional programming is sort of stateless, we can do this, to spread the computation across many such machines. So we could spin up on demand 360 cores if we wanted to really predict very quickly things that you'd want to know about what's going to happen to cancer patients. This project is a big success, but the business future of it is confidential. Suffice it to say, there will be an announcement in a while. And then thirdly, a company in the city of London, that's the equivalent of Wall Street for England. The city is a section of London. This company called OTAS built a product using our dev tool chain on Haskell called Lingo. And it's a stock market analyzer. Haskell happens to be a very strong language for parsing, oddly enough, because it turns out parsing is an example of functional programming. If I give you this, you tell me something about it. So in a few months with one developer, they wrote a commercial product, which is now in use by high-end stock traders moving millions of dollars at a time, to analyze what's going on in the stock market right now and produce natural language reports. And that's also deployed onto a variety of cloud machines. You'll notice that while I'm talking about the productivity and the quality that we got and the scalability of these apps, the concept of deployment keeps coming up. And that was a big surprise to us at FP Complete. We thought the hard part of software development was writing the code. And we discovered that deployment was much more important than we thought, which let that be the foreshadowing that I'm about to talk about DevOps. But before I do, let me just hit a few key points of what we've learned about functional programming. And in the interest of time, I've sort of crammed this all very close together. We've learned that functional programming allows you to find bugs at compile time because you're being very explicit to the programming language about what you're trying to do. We've learned that refactoring programs is not only easy in functional programming, but delightful. I know that's going to sound insane. That's like saying chopping onions is the best part of cooking. But honestly, I've done it myself. Refactoring programs is one of the most fun things you can do in Haskell. It's absolutely a delight. And as a result, the quality of software not only stays high in Haskell, but even goes up over time. It's absolutely amazing. In the algebraic constructs based on category theory, which is a form of advanced algebra that Haskell is based on, there is great abstraction. And we've learned that in Haskell and other FP languages as well, it's possible to write very abstract code, which provides immense reusability, with a separation of responsibilities, for example, between having a container, having members of the container, having a function that could be applied to members of that container, and doing something with those functions. All of those can be expressed in the abstract. And then you can go back in and define instances of those things independently and mix and match them. So if we have another talk about Haskell someday, we'll look into some examples of that, or you can go online and find some great examples. The abstraction in functional programming is great. We've also learned that functional programming works much better than anyone was telling us for service-oriented architecture. So if you're trying to design a modular application, what you want is a way of writing code that doesn't imply state. Right? You want a way to say, as long as you take these inputs and give me the right outputs, I don't care who you are, what you are, where you run, what language you're written in. Well, that's fundamental to the architecture of functional programs. So we learned that functional programming is a fabulous way to write SOA applications. Those go together very, very well. But the last lesson that I haven't said yet is that functional programming is very, very scary. It's the most scary new tool I've seen people adopt in my entire career in developing software. It's not scary when you know about it. When you get into it, you realize this is great. So it's scary like a roller coaster. At the end, you go, woo! But when you're in line, you go, oh crap, what am I doing here? What was I thinking? It's scary before you get on. So the number one reason teams don't adopt functional programming, despite the all true, all really that big benefits I've been telling you about, is that it scares people. We did a survey of over 1,200 Haskell users and would-be users and asked them, why aren't you using it more than you do in production? Because a lot of them aren't using it in production at all. They're just using it as their favorite language at home in the evenings, and they go back and program in something else when they're getting paid. And the number one reason people gave is, I can't convince my colleagues to give it a try. My colleagues are comfortable with what they're doing, and this is a new syntax, and it involves actually new concepts, not just changing a curly brace to a square bracket or something like that, really new concepts. And let's face it, we all have people that we've worked with, or maybe they work for us, that are pretty happy that they get paid to do what they already know how to do. And they feel like they're the master of their craft. And it's funny in such a forward-looking industry as ours, but people look backwards very, very quickly and start to say, I want to lock it in. I got mine. I don't want technology to move anymore. I figured out this tool. Well, functional programming is an enormous architectural movement that is happening now, but you will find probably a good quarter to half of all developers will resist even giving it a try, saying, I don't have time to think about something new. As Robert, who works at FP Complete, who's sitting right here, said to me a few days ago, it's like people are saying, don't talk to me about your fire extinguisher. I'm busy. I'm looking for a fire extinguisher. There really is a great sense of resistance among engineering teams to using a new tool. You can expect it. So if you want to look at functional programming, I strongly encourage you not only to look for the smartest people in your team, but also the most pro-risk, pro-reward type of people, as opposed to those who would never risk anything but just want to lock in what they learned 5 years ago. But once all the code is working, as I started to allude to, we found that deploying it onto servers and on the cloud was a much more significant issue than we thought it was. Not that it was hard to do with modern tools, but that the tools for doing it are very new and must be used. So a lot of people here are familiar with the term DevOps, the concept of DevOps. For anyone in the room or on the video who's not, a brief definition: DevOps is where development and operations comes together. And some people would just draw that with sort of two boxes, a development box and an operations box. But I think it's important, very important, to draw it as 3 boxes. There are all the things you do during the development of the software. So dev, test, machine learning if your software is based on data or if it helps to write itself, data science and all those things that are now starting to happen in the dev side of things. So all the creation of the software is in fact the first box. And the last box is in fact running the systems with the monitoring and the automatic scaling and the cloud features and so on. But the box in the middle is incredibly important, and we're going to talk about this box: the deployment of software from the lab or the developer's desktop onto servers, clouds, and clusters, and why that actually has to be done really, really well and is actually an important point of failure. So we at FP Complete, because we're a business about software technology, it's our job to go find out what's going on with people and what the obstacles are that they would like fixed. And so we actually do primary research, and we go out in person as well as online and meet with companies and ask them, both in depth and in numbers, what are your issues? And what we're finding out is that deployment is a really, really serious problem that is really an unacceptable state right now, is the number one problem in a lot of software teams. Could I just, by show of hands, ask if there's anybody here who has had serious issues with deployment working well during the past year or so? I'm seeing like literally 50% of the hands in the room, a little more than 50%. That's about what we're seeing too. So when we look at companies that are building proprietary software and then maintaining it over time, it seems to get worse and worse. People talk about software rot or code rot, where it's hard to maintain code over time, and functional programming, as I mentioned, is really good for fixing that. But far worse far worse, is server rot. And what's happening is the same problem as with functional programming. Servers are stateful. And people will go onto servers and modify them. Let's add an admin account. Let's change this database connection. Let's install a new file system. Let's patch this operating system. Let's upversion this application or just this component. And what you quickly end up with in the real world of production of software online are servers that are in a state no one has ever seen, ever. And we say we're going for quality, and then we put our end users on a server that is in an irreproducible and unknown state. We don't even know what that state is, and we certainly haven't tested anything in that state, and that's what we put our users on. So of course, that's not going to work. We need a better way to do deployments using automated, more intelligent systems based on modern DevOps. And when we talk to that minority of companies that have adopted better DevOps, and we'll talk about this in a minute briefly, but 100%, literally 100% of those we talk with are glad they made the investment. They're all saying it pays for itself many, many times over. And the solutions are the same across industries. There are some known best tools and practices in DevOps. This is not at all a black art. On the contrary, DevOps is giving people predictable success, the ability to routinely, anytime it seems appropriate, or even on a clock schedule that's set by the calendar and not by an engineering criterion, just routinely put new software on the servers all the time, every day or every week, instead of every month or every 6 or 9 months. And by doing this, you increase the cadence of engineering, you get features to users faster, and you avoid giant deployments, which are almost guaranteed to break because so many things change at once. But to do this, you must have predictability and reproducibility, and that means if it works in test, it works in production, and if it works in production, you're not going to break it through mutation. How do you make servers immutable then? How do you take the idea of immutability, do not change the state of something because then you couldn't do it in a different order and expect a good answer? How do you take that idea from functional programming and use it in DevOps? The answer is quite simple. Servers have gotten cheap and automation has gotten real. And therefore, instead of saying, I'm going to patch this server over and over again, we create a new server with a new state defined under source control, and then we tear down the old one. Imagine if instead of having to live with a broken arm that got patched and then healed, I could just build a new one of me that was exactly like me the moment before I broke my arm and go forward with that one. That would be nice. Not feasible with living organisms, but we treat servers as if they were these precious living organisms. They are not, especially now that we have clouds. They are easily reproduced. But until we automate and use proper tools to do our deployments, we're treating servers as if they were these surgical patients. Oh, I have this one system admin who knows how to come in and fix it when it does this thing. Well, congratulations, you just made an irreproducible server. What we want, and we learned this actually from the healthcare industry, where they want to be FDA regulated, and they want to say, we can reproduce this anytime you want. We know exactly where this output came from. Don't worry, we're not going to kill a patient by mistake. You want to have a well-defined engineering process and a well-defined automation process that brings up servers every time. And all of a sudden you realize, I'm not worried what my server is going to do, because the server that I just brought up from nothing looks exactly like the test server that I just brought up from nothing. I used the same script to bring it up. So automated, reproducible deployments are in fact the key to all of DevOps. We can talk about continuous integration, and we can talk about system monitoring, we can talk about lots of things. But deployments are the root of everything. And if there's one takeaway from my talk today is, if you do not have reliable automated deployments in your company, it is your job as a CTO to get them immediately. So that's what I just said. Continuous integration is, however, important enough that I'm going to pause. It's another piece of DevOps that happens way over to the left in that diagram, just before that first arrow. And I want to talk for a moment about continuous integration. How many people here believe that they're doing continuous integration in their teams? Only about half. That's really interesting. So to define continuous integration just for a second. Actually, does anybody here want to? We have a lot of people who know what it is. What's continuous integration? You already did one. Somebody else. Go ahead.
You have a CI server that has a set of automated tests, and every night, let's say when you commit your code, it'll automatically run it through those tests, and if everything passes, it pushes out a build and deploys it to, either a test server or production, depending on what you choose.
That's a great description, just for anyone who didn't hear it or on the video. You have a server that's doing a build and then running automated tests, and then if it passes all the tests, it's pushing that out to a test or production server automatically, perhaps nightly. Did I capture that about right? And so continuous integration allows us to say that there's always a running version of our software that's very up to date and recent. Why don't people do continuous integration? Because they haven't automated the tests, or they haven't automated the build, or they haven't automated deployment, which means it's not interesting to have a new version of the software too often, right? So automation with stronger tools gets us into a world where continuous integration makes a ton of sense, and where we can expect to put new versions of our software into production either as soon as they work or the very next time the clock ticks, whether that's once a day or once a week. If you're not using modern DevOps, you're just going to have to start. It's as simple as that. Functional programming, I love it, but you could go a long time before you ever touch functional programming. You probably have to use DevOps now for your dev team and for your end users. And if you do, you're going to realize that these tools allow you to achieve this set of trade-offs that we talked about. Look how high level I'm being. Look how there's no code on the screen. So my takeaways for today, before we switch to Q&A then, are very high level and very simple, because I don't want to dilute this with a bunch of detail that you're all smart enough to look up or you can ask me. Number one, the top takeaway that I really want this room to believe is it's all about tools. Everything we do is about tools. If your team isn't productive, if your software is full of bugs, if your customers aren't getting what they want, if everybody's upset and scared, it's about tools. Getting smarter will not fix bad tools. If you think about my picture of the axe and the saw and the CNC router table, right? There's no way to make that axe into a CNC router table. And if you just yell at the guy who's swinging the axe, swing it really, really carefully so you can make a micrometer pattern throughout this whole sheet of wood like the CNC table does. He's not even going to laugh at you. He's just going to quit because you're saying things that are impossible. We have to focus on tooling. It's a primary job of the CTO. And I'll say, I never looked back for a moment with regret at the time that I left my job running some other work to go build a whole tools group just for Microsoft. We made more success in less time than any other thing that I've ever done. Tooling is where you need to focus. In particular, please go look into DevOps immediately if you haven't right now. I've listed 2 websites that I would strongly encourage you to start at. Please look into functional programming if you are still writing new code, or if you have a modular enough architecture that your next piece of new code could potentially, if it were a good idea, be written perhaps in a new and different language. And I've listed 2 websites here that you can go to learn about functional programming. And finally, I do have a whole team of senior engineers who've been spending up to 5 years just soaking in these technologies. And if we can help you at all, we'd certainly be glad to. That's all I wanted to say today. So let's open it up to questions, because I know I didn't say enough about some things. Go.
Could you maybe address AWS Lambda and kind of how you see that play, or where that fits into the space?
So you want to talk specifically about serverless deployments?
Yes. Yeah.
Okay. So do you want to define it for people who don't know about it, just really briefly?
So I'm probably not the best person.
Okay.
I've only just read a little bit about it. We're not using it for anything, but one of the new products from AWS is, they call it AWS Lambda, and there is no provisioning of servers or any part of that. You're strictly providing the functional code. Here's this function, call this, do this, give it, and they will handle all of the DevOps for you, and scaling that up and down as needed to serve the load.
That's a great description. And if you can't hear it in the video, just go look up AWS Lambda. I guess he is being caught on mic, so that's great. So if you look at containers such as Docker, you find a technology that reduces the amount of implicit state that's supposed to be there before your app gets installed, right? You should be able to say, get me any virtual machine that's configured more or less this way, and I can plop this container down on it, and the container will include the file system and so on, libraries needed to run my application. So we're stripping down the amount of preconditions that are external to the software engineering process, the amount of magic that the computer doesn't know why you did it, but apparently it was done, and if it doesn't happen, nobody knows why. So Docker reduces that. Serverless takes that to an extreme and says there should be some files or databases in which you can declare every possible precondition needed for your code to run, so that a naked server can be used as a platform for running your code, and then that server can be wiped as soon as your code is done. So no state before, no state after. Again, it's a generalization of the notion of functional programming onto the notion of cloud DevOps. It's a lovely concept and a lovely technique. The key thing to understand about serverless is that it's applicable in terms of performance in very specific cases. It's for cases where getting your application going is inexpensive, tearing your application down is inexpensive, and your application in particular probably doesn't have to do a lot of binding to things that exist outside of its world. That statefulness, like talking to a database or having a lot of security set up or things like that. So if you just want pure functions to be executed, take these inputs and do a lot of math and give me an output, then, and it has to scale dynamically, then serverless is a good technique to look into, and AWS Lambda is one of several valid brands for serverless. Bearing in mind, Microsoft, Google, and other companies also have good clouds that we can use as well. Another question? Yes.
I can understand how you can do reproducible deployment of server code, server architecture. How do you handle databases?
Databases are a really key question. I intentionally omitted them from this. So usually when we talk about immutability, databases will be outside the scope of what's immutable, because the job of a database is to mutate, right? The whole point of it is that it holds state, it holds data that's been put into it. So in the two levels of immutability that we work with at FP Complete, in both cases we try to keep the real production database outside of that. Now there could be a reference database that doesn't change much, basically a static database, that could be part of the immutable device. But normally, we look at the database as being subject to I/O. It's part of the world, not part of the device, if you will, the distributed system that we're trying to deploy and manage. So when we redeploy a new version of the compute system, that might include user-facing servers, message brokers, system management servers, compute servers, firewalls, admin accounts, security settings, VPNs, VPCs, lots of things are inside this device, but they all have the character that they're really stateless resources. And the stateful resources that are not to be replaced every night sit outside of that entity. So we draw a big, big, big circle around this entity of all the things I listed and call that the device. Whether that runs on a cloud or on a private cloud or even on static hardware or VMs, that's the device. The database is not part of the device. The database is part of the world. That won't go away, because even if you have a different conceptual model than I do for databases, you still would have to deal with users. And users will appear the next day after you deploy with new questions and new inputs and demanding new outputs. So databases for us live in the same universe that users and state live in, rather than in the magical stateless universe that functional programs live in. One more? Yeah.
Yeah, so I'm trying to get an understanding of what the use cases are. You mentioned oncology and financial analysis, and obviously the function, you mentioned algebra, right? So is this for mostly data processing, data analysis, or what types of applications are good for functional programming?
Well, to begin with, functional programming is a generic software development technology. So we've written web servers, and people have written visualization programs and video games and programming languages and major websites. You can do basically, or scalable scientific computation. You can do whatever you want in a functional programming language. They are very much general purpose languages. That said, what are they really shining at? Where are they really standing out as particularly great languages? They're particularly great for processes that involve a lot of data handling. If a lot of data is moving through your system, and then is having a great deal of value added to it, whether it's parsing, cleansing, very advanced computations, routing. Erlang was invented actually as a programming language for routers, as it happens. So anything involving moving a great deal of data around and adding a great deal of value to that data, functional programming is very strong at. If I were to pick, and that happens, for example, in life sciences, advanced financial services, and high security web services. Those are probably the three top areas that we at FP Complete look at. But if I were to pick a second area, I would say functional programming is very good at reactive programming. Right? When a user does this, respond by doing that. And as such, because it's, again, a sort of definitional state transition diagrams. A lot of that, it turns out to be stateless, that we mistakenly think of as being about state, but it's actually stateless transition facts that we're programming. Interactive, sophisticated websites that have to be very fault tolerant and type checked at compile time instead of finding out days later that there's a missing resource or a type error are also very well written. And in fact, our head engineer is the lead of an open source project called Yesod, Y-E-S-O-D, which is a high reliability functional programming based website development system. So,
Would be good for AI and chatbots and things like that as well.
well, the most famous functional programming language in the old days was Lisp, which developed into Scheme, which is thought of primarily as an AI language. So that's a very, very emphatic yes. And you could argue that the stock market analysis software that I was mentioning is a type of AI, and you could argue that the machine learning aspects that we're seeing used in a lot of life science things are a form of AI. So you could argue that Watson could easily be written in Haskell, although it's not. So yes, emphatically yes, functional programming languages are an excellent choice for machine learning, pattern detection, and AI. Just didn't have time for those examples. Yes?
Can you give an example of some of the kinds of tools you built at Microsoft that gave you those productivity gains?
Well, bearing in mind this was many years ago, the team that I built and ran was responsible for the issue tracking system at Microsoft, the source code control system, which was amazingly scalable to deal with 2,500 engineer Windows project, the localization system, things like this. So really core engineering tools that today you would probably download an open source version of something like that, although it might not scale to Microsoft's scale. But we were solving the problems of the 1990s because that's when it was. Yes?
You mentioned that functional programming techniques let you create highly abstract code.
Mm-hmm.
Does that get in the way of bringing a new person into the team if you have a large library? Does it create a steeper learning curve for you?
What a great question. So does functional programming increase the steepness of the learning curve for new people in the team? The part about learning FP, if they're not FP programmers, certainly is obviously like any new tool, they're going to have to learn the tool that your team has adopted. But the code itself tends to be much, much easier to learn than imperative traditional code. Why would that be if it's so different and sophisticated? Well, two reasons. One, the high level of abstraction in functional programming allows a very clean separation of responsibilities. So if I have a piece of code that operates on entities that live in a container, that code doesn't need to know anything whatsoever about the nature of that container. And similarly, if I have a piece of code that traverses a container, let's say I'm doing a breadth-first search on a B+ tree, that code doesn't need to know anything whatsoever about the nature of how that container is actually physically stored or what's inside of it, or even in what order the code has to be executed unless it wants to assert that. So the separation of responsibilities makes each function a lot cleaner than it typically would have been in the past. Secondly, and more importantly, is the immutability that we heard about at the beginning. Thank you for that great definition up front about functional programming. The fact that when you look at a function, you know it's going to do what it says it does and nothing else slashes the problems. And that, by the way, is part of why I don't really recommend Scala, because in its effort to be Java compatible, Scala has allowed functions to maintain hidden state, which means oh, good luck if you're the new person on the team, and an operator is overloaded and doing who knows what, who knows where, literally could be almost anything. That's completely unacceptable, and that would be a compile time error in a pure functional programming language. So when you're using, let's say, real functional programming as opposed to a language that imitates the syntax of functional programming, what you find is that it's much easier to join a project because you're never worried, oh gosh, what's going to happen secretly when I call my colleague's function? The answer is nothing, which is a beautiful answer. Another question? Yes?
How are you measuring productivity when you're looking at the productivity gains of functional programming versus a different language?
Well, we and most teams look at productivity in a very simple way. Time to market for a given size team for a given amount of complexity in the user-facing capabilities that they're trying to deliver and at a given quality level. So if you lock down functionality, complexity, quality level, size of team, and then say how long did you take, or lock down how long you take and then say size of team. So that's how we measure it. So when we say something is 100% more productive, we're either saying the same size team can do it twice as fast, which is probably true. In many cases, it's better than that. Or less than half the size team can be used to deliver the same amount of function at the same quality level in the same amount of time.
So using like function points or something to measure?
You can use function points and you can certainly use formal methods like that, but I have to be frank as a guy who's sort of been around the block more than a couple times, as attested to by my hair color, nobody does in reality. People really get experienced enough that they can look at specs and they can say, this functional spec looks like about twice as many features as this functional spec. Or they can say, this program is extremely similar to that program that I wrote before, which took 3 times as long to write. In addition, people can also, this is something people do, and which I'm a big fan of in large teams that can afford the overhead for the infrastructure, measure how people are spending their time. So you can do research projects where you say, for a week, let's all record for every half hour what we did. And then let's go back and look. And studies like that have shown that software engineering teams are spending 50 to 55% of their time on bugs and defects. And that if you go to functional programming teams, that number is absolutely slashed because those are found at compile time far more often. So those are the ways we measure it. Etienne, how are we on time?
We're good on time.
Okay, go ahead.
What are some of the downfalls of functional programming? Like, why wouldn't every person in here not go and say, we need to do functional programming right now?
Right, why doesn't everybody just use functional programming right now? The number one downfall by far is that and downfall is probably too strong a word, but let's say impediment, is that functional programming is so conceptually different from how people write code today. The notion that you cannot get around a problem through a mental trick of saying, if I had a piece of state, then I could not have to tell the computer what I'm trying to do. I'll look at that piece of state later and I'll figure out what I was trying to do. You're not there in the functional program. Functional programs exist in abstract statements of fact that are timeless. And so you can't say, I'll reach in and do something, because that implies that you're present in time. So the mental tricks that programmers have learned ever since probably literally the first day they learned to program don't work. Let me give you an example of a day one issue. Let's say you were going to traverse the members of an array and, I don't know, double them. Right? In traditional programming, that might be something you'd do during the first week. You'd have maybe a counter, maybe the variable I, and you'd say I equals 0, do something to element I, increment I, do something to element I, increment I, do something to element I, until I is too big, and then you stop. Right? That'd be a normal way to write code at a low level. Certainly that's how you'd write it in assembly language. But it's also carried over into allegedly modern languages like Java or C++. What's I? What is that thing? It's not present in the problem at all. It's an abstraction that says, I believe there are various elements in my array, and I believe we should look at all of them. Okay, that's a meaningful statement, but saying there's this thing I that you keep adding 1 to and testing the value of, that's nonsense. That's the programmer trying to be smarter than the computer. Can we not say to a computer of all things, do this to the elements of an array? Is that not something computers have in hardware? Well, it is actually. It's built into the hardware. So we write programs wrong. We write them as if we were trying to make a pathetic little PDP-11 in 1972 in assembly language do something using some little trick that makes the computer do stuff. And then the compiler, and I used to run the compiler group at Microsoft, the compiler will try to strip that out. It'll try to say, oh, wait a second, I know. That's your silly way in the semantics of this language to say you really wanted to do this to all the elements of the array, but you use this old-fashioned style of coding, so I'm going to try to, if I can, to optimize it out, and I'll just say do this to all the elements of the array and hardware if it's compatible with the hardware. So we do all these tricks that are so archaic, even the computer doesn't believe them, but it's how we program. So to answer your question, anyway, getting back to it, what's hard is when you start doing functional programming, you're expected to actually make true statements about the output you wanted and how it's defined. And we spent so many years as software developers learning how to lie and how to make all these little tricks to get the computer to do what we wanted, that it's a huge mental exercise for the first couple of months to say, oh, I don't have to say that. I can just say, do this to all of those in the optimal way. That's a lot of unlearning to do. And that's why people get intimidated, because they say, I thought I was good at this, and now my tricks are irrelevant.
So what would you say the unlearning curve is then?
I'd say to write basic code, like really, really simple programs in, let's say, Haskell or Clojure, you're looking at just a couple of days. But to write production quality code, if you haven't started and you're joining a team that does know a functional programming language, you're probably looking at a good 6 weeks. And if you're the very first person in your team and no one has ever looked at functional programming and you don't have a mentor and you're kind of going it alone with a book, then you're looking at a good couple months. Yeah.
How would you compare this to taking a sequential programmer and moving them to something that I'd say was stateless, like VHDL?
Well,
Is that fair?
yeah, so I mean, VHDL is in some ways a functional programming language, as is Excel. I mean, there are a lot of familiar tools that are secretly functional programming languages. So how would I compare this to taking a programmer and teaching them VHDL? I'd say it has a lot in common, because in both cases you're defining components that say, given these inputs, make these outputs. I can't tell you later to do something different, because in VHDL it's going to be locked in hardware, and in Haskell it's going to be locked in math at compile time, after which it's going to be optimized in ways where if that's not what you meant, too bad, because that's the optimization we're going to do. So yeah, it's very much like learning VHDL. Oh, no, probably a little easier, because it's still software, and you still have things like variables in memory and function calls and things that you're very familiar with. So probably a little easier, but conceptually similar to learning a hardware design language, yes. Yes?
Have you noticed any big changes in the talent acquisition strategy of moving from imperative programming to functional programming? Because, you know, like you said, it's a big, scary job for most people. Are you better to take an imperative programming team and train them? If you try to, you know, message and advertise a job like that, are you going to have issues finding those people? What does the candidate pool look like for those kinds of developers?
I'd say there's more. I'm very, very big on the talent issue. So I think there's more than one issue in your question. What's it like to acquire and build a team for functional programming versus if you just stick with the tools you're using today? So I'll give you a couple different points, a couple different bullet points of answer. One, we and some other companies have found that offering the ability to work on functional programming is a great recruiting tool. We've even seen cases where a VP decided to allow the use of functional programming specifically because they wanted to hire a certain genius talent person, and that person said, I will only come if you will allow me to do my work properly in functional programming. And so the VP says, fine, whatever, you crazy, you know, and then it turns out to work great. But that sometimes is what puts it over. Sometimes there's just an advocate, if you will. Getting the company to adopt functional programming is not terribly hard, because the proven business benefits are there. The budget compared to what you get, it's a no-brainer. As a CEO, I could easily recommend it to just about any CEO. So it's really down in the bowels of the team where you have individual people saying, I don't know if I want to learn a new tool. And I'll be honest, it depends on the caliber of people in the team. If you have people who love learning and who got into software because it allows them to use their brain instead of just brute force, it's one of the most fun things you can learn, and it's a treat and a delight. I mentioned the person who I resonate with who said, now when I have to use Java, I feel like I'm being punished. It's so much worse than what I do every day in Haskell. It's really night and day. So it's a delight once you learn it. But if you have people who don't like learning, who think that learning is like, you know, drinking pure lemon juice, you know, don't think of it as lemonade, then they're not going to like any new tool. And functional programming is certainly, for most people, a new tool. Yes?
So do you, just building on that, so do you think that it's easier or better to take imperative programmers and motivate them, convince them, get them open to learning functional programming, or start fresh? And I mean, do you need to know imperative programming to actually pick up functional programming, or could you start absolutely fresh?
There are a couple of universities that have switched their computer science curricula to begin with functional programming. I think it happened first at MIT and then at one of the universities in Australia. You know, you can absolutely learn computer science from scratch on functional programming. This is part of the confusion people have, is so many of us learned, you know, Haskell or Java or something else, that we forget that that's not computer science. That's just a tool that was used at the school we went to. You can absolutely do it. In fact, a slightly better job.
Should we be doing it at boot camp level?
We probably should be doing it at boot camp level, yes. There's nothing hard if you have learned imperative programming about learning functional programming once you're willing to put down your assumptions and say, what if there were a better way? What if, hypothetically, in the case of Haskell, what if a consortium of 7 major universities, including Oxford, Cambridge, Glasgow, Yale, and several others, spent 25 years trying to develop a better way of programming? Is there a chance that maybe it is actually good? If you can get people to just sort of, you know, put down their resistance and turn off their immune system for 24 hours to take a look, they usually love what they see. But it all comes down to the personalities and how the team has been managed, and if I dare say, as an executive, how people are treated. Right? Because ultimately, if people say, my company loves me and they're going to take care of me and they're going to get me over this hump, as opposed to, I'm terrified that if I don't pick this up in 4 days, I'm going to be fired. Right? So people have to know you've got their back. You're there to make them more successful. The tools are there to make them more successful, not to take their job, but to take off their plate the things that are not about delivering value to your customers. And by the way, if I could make the connection again, saying I said these are two tips of the same iceberg, the same is true with DevOps. When we at FP Complete go to different companies who are struggling with deployments in DevOps, what we say is, look, what do people pay you to do? Do they pay you to operate this server, or do they pay you to deliver some kind of a software capability that helps them run whatever they're doing as a business or as a science lab or whatever, right? They want these problems to go away. And so if you say, when this problem goes away, your job is going to be much better, then people get very excited, as opposed to when these problems go away, we don't need you here anymore because you were the janitor for these problems, right?
We're not going to hire as many programmers in the future because we're that much more productive.
You could argue that we're not going to hire as many programmers. I would argue differently. I would argue that functional programming is one of many ways, and so is modern DevOps, that we're addressing the global shortage of IT talent by saying there are so many unfilled jobs. We have to address the cost of getting the software done when there's no way to fill the jobs. Well, what if we could take our existing team and make them into superheroes? Wouldn't that be better for everyone? Yes?
Just to answer what you said, Michael, about training people at boot camp level. In that, the Learn Academy here in San Diego is starting to teach functional languages and functional web frameworks.
Yeah. They're a member of our CTO.
And one of the things that we've done a few times at FP Complete is just to temporarily join somebody's engineering team. Right? We'll send an engineer or two and say, look, be part of the, be the mentor. Go be a part of this team for a few weeks, and then sort of taper down over a few months, maybe as a remote member of the team, and just transfer that knowledge over. Another thing we do differently is to say, maybe bring in some experts to build a component, maybe an SOA, one piece of service-oriented architecture that's separate, and then show the team how it was built. Transition the tools over to them and say, okay, we've done one. Now it's integrated into your system at runtime. You can see how it works. You can see the source code, our coding standards, our dev tool chain. It's all there. Now you do the next one while we stand next to you. Right? And then the third one will be on call to give you a little bit of consulting. And then the fourth one, you know where we are if you need us, but you got this. So there's kind of a build, operate, transfer way of spreading the knowledge. And I think of myself, part of why I'm here today, I think of myself as being in the transfer business, the transfer of new technology from the sort of advanced realm where people don't know about it to companies that are building stuff.
Okay.
Yes?
How does it play with proof systems like TLA+? It seems kind of similar.
Yes. Yes. How does functional programming relate to proof systems? Very, very closely. In fact, there's a post on the Haskell Reddit just yesterday talking about letting the Haskell compiler prove that two programs are identical. There are also exercises where people write whole programs in the type system, where custom types are so powerful that you can actually solve your problem at compile time and never have to run it. That's quite extraordinary. And running can just be print the answer. Which means the work was done by the compiler. So proof systems are actually, to some degree, if you will, built into the better functional programming compilers, because what you want to do is establish the true meaning and equivalence of different statements that might have been done in the source code using different syntaxes, but actually meant the same thing at an optimization time can be shown to be the same. Let me give you actually, I'm going to build on your point for a second to talk about one example that's very non-intuitive. In functional programming, it's very common to use recursion. So you might say, like, the function to sum a list is like you do in Lisp. Take the head of the list and add it to the sum of the rest of the list. So, sum equals head plus sum of tail. And then sum of an empty list is 0, and then you go just recursively, you're done. That's the sum function. But you look at a thing like that and you say, wait, there's no iterator. Oh, this is going to be so slow. I'm going to pile up on the stack all these function calls. Oh, this is a stupid way to define this. No, because the compiler knows what you did. You've semantically, rather than through a hidden made-up magic variable called I, defined the meaning of what you were trying to do. That allows the compiler to completely optimize it. And the code at runtime, if you disassemble the machine language that gets generated, because like in Haskell, it's native code that comes out the back through the same backend that C uses, LLVM, you'll find that the same machine language was generated in response to that recursive definition of sum as a definition using a hidden variable I. Because in both cases, the compiler can prove that that's equivalent and that it can be done in a different way and still yield the same output. So proving equivalence or proving certain theorems is to a limited degree built in at compile time in the true functional programming languages, which again is why you can't be leaving side effects in. Because if I want to reorder something, but I say, well, every time I incremented I printed it, well, what happens when I'm running on an 8-core system and I'm incrementing 8 different versions of I? right? Then what's going to come out? Wouldn't work anymore. So being side effect free is crucial to being provable. And the only reason provers can ever run on traditional imperative programs is if they can be converted semantically into functional programs inside the tool, which is often impossible due to side effects, I/O, database access, state access, all built into the code irretrievably, which is why it's then hard to join the team on a traditional code base. Any more questions? All right, I think that does it. Thank you, Etienne. Thanks for having me.